Hey everyone, welcome to this course on feature engineering. If you have ever wondered why two machine learning models using the same algorithm can produce very different results, the answer often comes down to one thing: the quality of features. Over the next 8 videos in this series, we will build a very solid understanding of feature engineering, starting with the fundamentals and gradually progressing to more advanced techniques. Along the way, we will learn not just how different techniques work, but also when and why to use them in real world machine learning projects. And this course is not just theory. By the end of the program, we'll apply everything you have learned in a comprehensive industry aligned capstone project. We will work on a real world dataset and we'll build an end to end feature engineering pipeline. And we'll also gain hands on experience solving problems similar to those you will encounter in a professional data science role. Most importantly, we will finish this course with a portfolio ready projects that you can showcase to your recruiter and hiring manager as evidence of your practical skills. So, let's get started. So this course is divided into total of 8 modules, with each module building on what's learned in the previous one. Here is what we will be covering throughout this course. We will start with overview of feature engineering, then we will understand various numerical data and how to handle them. Then we move on to general feature engineering techniques and dimensionality reduction techniques. After that, we will read and understand about techniques related to data, text data, image data, time series data, and finally, we'll also understand what automated feature engineering is all about. So let's get started with module 1, that is overview of feature engineering. This module lays the foundation for everything we will learn in the rest of the course. Before we start transforming features or building sophisticated machine learning pipeline, it is important to understand why feature engineering matters in the first place, what problem it solves, and how it impacts model performance. We will learn these concepts through practical examples and real world case studies. So the ideas are not just theoretical, but they are easy to relate as well. So, in this module, we will start by understanding what features actually are, why they matter, where feature engineering fits into the overall machine learning lifecycle. From there, we will clarify the difference between data preprocessing and feature engineering through a practical case study. Next, we will explore various key goals of feature engineering and different ways features can be created, transformed, encoded, and selected. We will then discuss why feature selection is so important, especially when working with very large data set. Finally, we will look at the challenges of high dimensional data. We'll understand the curse of dimensionality and wrap up by learning how different machine learning models determine which features are most important. So, let's start with module 1, section 1 today, that is Introduction to Feature Engineering. Let's begin with a simple question: what exactly is a feature? When we work with dataset, not every column is automatically useful to a machine learning model, right? Some columns can be used directly, while others needs to be cleaned, transformed, combined with other information before they become meaningful inputs. So in machine learning, a feature is simply a measurable property or characteristic of an entity that helps a model make informed predictions or decisions. You can think of feature as a piece of information that model runs from. The better the quality and relevance of these features, the better the model's chances of making accurate prediction. The easiest way to understand feature is always through an example. Think of feature as a measurable characteristic of a thing we are trying to analyze, which is also known as entity. For example, if the entity is student, the useful features might include attendance, percentage, or quiz score, right? But if the entity is a customer, useful feature might be the age of customer or the monthly spending. Similarly, for a house, features could be its area or number of rooms. For a bank applicant in the loan approval problem, the features could be his or her income, credit history, etc. That will help model assess the applicant credit worthiness. You did you notice the pattern here? The entity changes depending on the problem, but features are always the measurable piece of information that describes that entity and helps the machine learning model make better decision. Let's understand this with a real world example. Imagine you are a bank manager reviewing a loan application. A customer has applied for a loan, and your job is to decide whether the loan should be approved or rejected. So, to make that decision, you will look at several pieces of information about that applicant, right? Such as income, credit history, age, existing debts, and perhaps even the employment status. But here is a key question: do all of these factors matter equally? Probably not. Some features have a much stronger influence on the final decision than others. Identifying these important features is exactly what feature engineering and feature selection helps us achieve, allowing machine learning models to make more accurate and reliable prediction. So now that we understand what features are, the next obvious question is, where does this feature engineering fit into the entire machine learning workflow? To answer that, let's look at the machine learning pipeline itself. Now, think of this pipeline as the journey that takes us from raw data to a machine learning model that can solve real world problems. While the steps happen in sequence, the process itself is continuous. As new data becomes available, we revisit and improve the model, making the pipeline a cycle rather than a one time process. It all starts with data collection, where we gather the raw data needed for our problem. The next obvious step is data pre-processing. Here we clean the data, we handle the missing values, we remove inconsistencies, and prepare it for further analysis. Once the data is clean, we move to next stage, that is feature engineering. This is where we transform the pre-processed data into meaningful features that captures useful patterns and information. You can think of feature engineering as a bridge between prepared data and a machine learning model. The quality of these features often has a great impact on the model performance than simply choosing a more advanced algorithm. After feature engineering, we move on to model training, where we select an appropriate machine learning algorithm and train it using the engineered features. Next comes testing and deployment. We evaluate how well the model performs on unseen data, and if it meets our expectation, we deploy it to our production. Finally, we enter the monitoring and maintenance phase. Over time, data patterns can change, causing models' performance to decline. So, we continuously monitor the model, collect new data, refine features, and retain the model when necessary, and repeat this entire process. So, as you can see, feature engineering sits between data preprocessing and model training. It plays a crucial role by converting prepared data into informative features that enable machine learning models to learn effectively and make accurate predictions. In practice, well engineering features often contribute more to model performance than the choice of algorithm itself. Now that we have seen where feature engineering fits into the machine learning pipeline, let's understand what actually happens during this step. The process is quite straightforward. We start with clean and pre-processed data as the input. The goal is to transform the data into meaningful task specific features that a machine learning model can learn from. So, in other words, the output of feature engineering is not more data, it's better data, quality data. The ultimate objective is twofold. First is to improve the model's predictive performance, and second, to make the model easier to understand and interpret by ensuring that the features captures the most relevant information out of that data. So, formally, feature engineering is the process of using domain knowledge along with the mathematical and statistical techniques to transform raw data into meaningful features that can improve the performance of machine learning models. Notice one important phrase in this definition: domain knowledge. That's because feature engineering is not just about applying formulas or writing codes, it also requires understanding the problem you are trying to solve. The more you understand the business context and business domain and the data, the better the features you can create. This is why feature engineering is often called as the art of data science. While machine learning algorithms follow well defined mathematical rules, designing useful features requires creativity, intuition, and a deep understanding of both the data and the problem domain. It is this combination of science and human insights that makes feature engineering such a powerful skill. Now let's move on to the next concept, that is data pre-processing versus feature engineering. At this point, it is important to understand the difference between data pre-processing and feature engineering. These two terms are often used interchangeably, but they serve very different purpose. Both involve transforming data, but the intention behind that transformation is completely different. Think of it this way: data pre-processing prepares the data for machine learning, but feature engineering improves the data for machine learning. A simple rule of thumb is pre-processing fixes data problem, feature engineering adds business value. So, during pre-processing, we are focused on making the data more clean and usable. This includes handling missing values, removing duplicates, correcting inconsistencies, or scaling numerical values so that algorithm can process the data correctly. Whereas feature engineering, on the other hand, goes a step ahead. Instead of just cleaning the data, it creates or transforms features in a way that helps the model better understand the underlying problem and make more accurate prediction. So here is an easy way to decide which category a transformation belongs to. If a transformation simply makes the data structurally usable by a machine learning algorithm, then it's a data preprocessing. But if that transformation introduces meaningful task specific information that improves the model's ability to learn, it's feature engineering. That distinction is important because pre-processing ensures the model can learn from the data, whereas feature engineering helps the model learn better from the data. Let's make this distinction more concrete with a simple example. Imagine you are building a machine learning model for a bank to predict whether a loan application should be approved or not. And one of the column in your dataset is obviously applicant's date of birth. Now you ask yourself, does the bank really care about the exact date someone was born? Not really, right? What the bank is actually interested is in the applicant's age, because age is much more relevant when accessing factors such as financial stability or credit risk. So instead of using date of birth directly, we can calculate the applicant's age using a simple transformation. So what we'll generally do is basically we'll extract the year from the date of birth, and from the current year we'll subtract that year, and we will arrive at the age of the applicant, right? So notice what's happening here. We are not fixing a data quality issue. The date of birth is already clean and perfectly valid. Instead, we are converting it into a new feature that carries more meaningful information for the prediction task, right? This transformation uses our understanding of banking domain to create a feature that is more useful for the machine learning model. That's exactly what feature engineering is all about. It's not just transforming data, it's transforming data in a way that makes it more relevant for the problems you are trying to solve. In this example, age becomes the feature the model learns from. Why? Date of birth simply serves as the raw information which is used to create it. The interesting part is that the exact same transformation can be either pre processing or feature engineering. The difference is not the code, it's the intention behind it. So let's take two cases here. We'll see when it is a data pre-processing and when it is a feature engineering. So let's start with case 1. Suppose your machine learning algorithm does not accept date values and only works with numeric inputs. In that case, you convert date of birth into age simply because the model needs a numerical value, right? You are not making any assumptions about whether age is important for the prediction or not. You are just making the data compatible with the algorithm. In this situation, the transformation is data pre-processing because its purpose is purely technical. Now moving on to case 2, when is it a feature engineering? Now consider a different scenario. You are building a loan approval model, and based on your understanding of banking, you know that age influences financial behavior and credit risk. Younger and older applicants often exhibit different borrowing and repayment patterns. So you deliberately create the age feature because you believe it will help the model to make better predictions. Here, the transformation is driven by domain knowledge, not the technical requirement. The goal is to provide the model with more meaningful signals. That makes it feature engineering. So remember the key idea. The code may be identical, but the purpose behind the transformation determines whether it is a pre-processing or whether it is a feature engineering. So that's one of the most important distinctions to understand before moving forward. Welcome back to part 2 of module 1. In part 1, we covered the basics of feature engineering, We also saw difference between data preprocessing and feature engineering through some case studies. And we also saw where does feature engineering fits into the overall machine learning workflow. Now, let's understand key goals of feature engineering. Now that we know what feature engineering is, let's answer an important question. Why do we invest so much effort in it? The answer can be summarized using a simple acronym ATOMS, atoms. These are the four primary goals of feature engineering. The first goal is accuracy. The quality of a machine learning model depends heavily on the quality of the feature it learns from. When we create features that captures meaningful pattern in the data, the model has better information to work with, leading to more accurate predictions. The second goal is tackling overfitting or simply reducing overfitting. So real world data are often very noisy and may contain irrelevant or very redundant information. So if we feed all of these into the model directly, it may start memorizing the training data set itself instead of learning general pattern. So by removing unnecessary features or retaining only the most relevant one, we help the model to generalize better to new and unseen data. The third goal is optimizing training or accelerating the training process. Fewer, better features means that model had very less data to process, reducing unnecessary dimensions or eliminating sparse or redundant feature often results in faster training, lower computational cost, and more efficient machine learning pipelines. And the fourth goal is and stands for model simplicity. A model does not always need hundreds of features to perform well. In many cases, a carefully selected set of meaningful features allows a much simpler model to achieve performance comparable to much more complex ones. Simpler models are always easier to understand, easier to explain, and often easier to maintain in production as well. So, remember the acronym A is for improving accuracy, T is for reducing overfitting, O is for optimizing or accelerating training, and M is for model simplicity. So these four goals captures the essence of why feature engineering is such a critical part of every machine learning project. Moving on to our next topic, what are various types of feature engineering? So let's see that. So far, we have discussed what feature engineering is and why it is important. The next question is, what kinds of feature engineering techniques are available? Broadly speaking, almost every feature engineering technique falls into one of these four categories. An easy way to remember this is with the acronym CTES. The first is feature creation, where we generate entirely new feature from the existing data using domain knowledge or mathematical relationship. Next is feature transformation, where we modify existing feature to make them more suitable for machine learning. This could involve scaling, normalization, or applying mathematical transformation. The third category is feature encoding. So many machine learning models and algorithms work only with the numerical data. So this step converts categorical variables such as cities, color, or product types into a numerical representation that models can understand. And finally, we have feature selection. Here, the objective is to identify the most informative features and remove those that are irrelevant, redundant, or noisy. This not only improves model performance but also makes the model simpler and very easy to interpret. So, let's begin with our first type, that is feature creation. So, as the name suggests, feature creation is all about creating new features from the information we already have. Instead of collecting additional data, we derive new variables by applying mathematical formulas, combining existing features, or using our understanding of problem domain. The key idea is simple here. The new feature often carries more useful information than the original data alone. Let's look at a few examples here. Earlier, we saw how date of birth can be converted into age. Age is usually much more relevant for prediction than the exact date of birth, making it a classical example of feature creation. Another common example is body mass index or BMI. Instead of looking at person's height or weight separately, we combine them using a mathematical formula to create a single feature that better reflects overall body composition. Similarly, in real estate application, we can create a new feature called price per square foot by dividing properties price by its area. This derived feature often provides a much better basis for comparing property than looking at price alone. Notice a common pattern across all these examples. We are not creating any new information. The information already exists in the dataset. What we are doing is representing it in a way that's more meaningful to the machine learning model. So that's the essence of feature creation. It transforms existing data into features that better captures the underlying pattern of the problem. Moving on to our second category, that is feature transformation. So, unlike feature creation, we are not creating new features here. Instead, we are changing the values of existing features to make them more suitable for machine learning algorithms. The goal is to modify a feature's scale, distribution, or representation while preserving the information it already contains. Two of the most common transformation techniques are standardization and normalization. These methods rescale numerical features so that different variables can be compared on a common scale, which is especially important for many machine learning algorithms. Another widely used transformation is logarithmic transformation. Consider a house price dataset. Property prices are often highly skewed, with a few extremely expensive houses, creating a long tail in the distribution. So, instead of using the raw prices directly, we can apply a logarithmic transformation such as log of price. Right. So, what this does is this will compress very large values while leaving smaller values relatively unchanged, making the distribution much more balanced. As a result, the model often learns pattern more effectively and becomes less sensitive to extreme values or the outliers. So, unlike feature creation, where we generate entirely new feature, feature transformation focuses on improving the existing features by changing how they are represented, making them easier for machine learning models to learn from. The third category is feature encoding. So far, we have worked mostly with numerical data, right? But in real world data set, many features are categorical, meaning they contain text values rather than numbers. For example, a customer's city or a product's category or a person's marital status are all categorical features. The challenge is that most machine learning algorithms cannot perform mathematical operations on text directly. Algorithms such as k nearest neighbor, k means clustering, logistic regression, linear regression, SBM, XGBoost, gradient boosting, and neural networks all expect their inputs to be numerical. So that's where feature encoding comes in. Feature encoding is basically a process of converting categorical variables into numerical representations so that machine learning models can understand and process them. There are several encoding techniques, but two of the most commonly used in the industry are label encoding and one hot encoding. With label encoding, each category is assigned a unique numerical values. For example, the categories such as low, medium, high may be represented as 0, 1, and 2. Similarly, the size of t-shirts like small, medium, large, XL can be represented by 0, 1, 2, 3, and so on. So that is with respect to label encoding. With one hot encoding, instead of assigning numbers, we create a separate binary column for each category. This avoid introducing an artificial order when no natural ordering exists. We will study about these techniques in detail later in this course. For now, the key takeaway is very simple. Whenever your dataset contains categorical information, feature encoding transform those text-based values into numerical features so that machine learning algorithms can work on it. Without this step, many ML models simply cannot use the categorical data at all. Let's understand one of the most widely used encoding techniques, that is one hot encoding. Imagine your dataset has a column called color and the values are red, blue, and green. So a machine learning model does not understand these words. It only understands number. So one option might be to assign numbers like red equal to 1, blue equal to 2, and green equal to 3. But this creates a problem. The model may incorrectly assume that green is somehow greater than blue and blue is greater than red, even though colors have no natural order. So to avoid this, we use one hot encoding. Instead of replacing the categories with numbers, we create a new binary column for each unique categories. So the single color column becomes three new columns like color red, color blue, and color green. Now, if a particular data point has the value blue, the encoded representation will look something like this, where red will be equal to 0, blue color will be equal to 1, and green color will be equal to 0. Notice what happened here. Only the column corresponding to the actual categories is assigned as 1, often called hot, while all the remaining columns are assigned 0 or cold. So that is why the technique is called one hot encoding. Exactly one column is hot for each observation. The biggest advantage of this approach is that it does not introduce any artificial ordering between categories. Every category is treated as completely independent, making it a safe and effective encoding method for all nominal categorical variables. That's why one hot encoding is one of the most commonly used techniques while preparing categorical data for machine learning models. The fourth and final category is feature selection. Unlike feature creation or transformation, we are not creating or modifying features here. Instead, we are deciding which features are worth keeping. Feature selection is the process of identifying the most relevant feature for a prediction task and removing the rest. Now, you might wonder, why remove features at all? Isn't having more information always better? So, not necessarily. In fact, irrelevant or redundant features can confuse the model. It can increase computational cost or even hurt the prediction accuracy. That's why, in many cases, less is actually more. Feature selection is important for two main reasons. First, it reduces the dimensionality of dataset. With few features, models train faster, it requires less memory, and are often less prone to overfitting. And second, it improves the model interpretability. When a model relies on a smaller set of meaningful features, it is much easier to understand how it is making those predictions. So, how do we decide which features to keep? Okay, so we use statistical and machine learning techniques such as correlation analysis and mutual information to measure how strongly each feature is related to the target variable. We'll explore all these methods in detail later in this module. Now that we have discussed feature selection, a natural question arises, right? How do we decide which features are actually important? There are several techniques for measuring feature importance, but in this module, we will focus on two of the most commonly used methods. First one is Pearson correlation, and second one is mutual information. Pearson correlation is used when we are working with numerical features. It measures the strength and direction of linear relationship between feature and the target variable. In other words, if two variables increases or decreases together in a straight line pattern, Pearson correlation does a good job of capturing that relationship. However, many real world relationships aren't perfectly linear. That's where mutual information becomes very useful. Unlike Pearson correlation, mutual informations work on both numerical as well as categorical features. More importantly, it can capture nonlinear relationship as well, making it a much more flexible measure of feature importance in many practical machine learning problems. So, for now, think of Pearson correlation and mutual information as two different lenses for measuring how informative a feature is. We will revisit all these techniques in much greater details later in this module, where we will understand how they work, when to use each one, and how to interpret the result of both the mutual information and the Pearson correlation. Next up is one of the most important concept called curse of dimensionality. So let's see what exactly it is. So far, we have talked about creating, transforming, encoding, and selecting features. But as the number of features grows, machine learning models begins to face a new challenge called curse of dimensionality. To understand this concept, first answer a simple question. What do we mean by dimensionality? In machine learning, dimensionality simply refers to number of features or columns in the dataset. So, if your dataset has 5 features, it is called 5-dimensional data. If it has 100 features, it is called 100-dimensional data. So, in general, every feature adds one dimension to the dataset. Let's visualize what that means. With one feature, every data point can be represented on a single number line. That's one-dimensional data or 1D data. Add a second feature, and each data point now has x and y coordinate, placing it on a two-dimensional plane. Introduce a third feature, and the data moves into three-dimensional space, where every point is located inside a cube using x, y, and z coordinate. Now imagine adding dozens or even hundreds of features. Of course, we can't visualize a 100-dimensional space, but mathematically, every additional feature introduces another independent axis. Instead of lying on a line, plane, or inside a cube, the data points now exist in a high-dimensional feature space spread across many axes. This increase in dimensionality creates several unexpected challenges for machine learning models. In the next few slides, we will explore why simply adding more features doesn't always improve a model. In fact, beyond a certain point, more dimensions can actually make learning much harder for the machine learning models. So, this phenomenon is what we call it as curse of dimensionality. Now that we understand what dimensionality means, let's look at the downside of having too many dimensions. This brings us to a fundamental concept in machine learning called as curse of dimensionality. Despite the name, this is not a single problem. Instead, it refers to a collection of challenges that begins to appear as the number of features in dataset increases. These issues are unique to high dimensional data and are either absent or much less severe in low dimensional settings. In other words, simply adding more features does not always make a model better. Beyond a certain point, it can actually make learning much more difficult, very less reliable, and more computationally expensive. The curse of dimensionality has four major consequences. The first is distance matrix fails. What does that mean? As the number of dimensions increases, the notion of distance becomes less meaningful, making it very difficult for distance based algorithm to distinguish between similar and dissimilar data points. The second is data sparsity. In high dimensional spaces, data points becomes increasingly spread out, leaving very few observation in a local region of the feature space. So that is called data sparsity. The third consequence is an increased risk of overfitting. With too many features and limited training data, models can begin memorizing noise instead of learning meaningful pattern out of the data. And finally, increased computational cost. So more features means more calculation, means higher memory requirement, and hence longer training times. So these are the four technical consequences of curse of dimensionality. The first one is distance matrix fail. Second one being data becoming more sparse and sparse. Third being overfitting risk, and fourth become increased computational cost. So, next we will examine each of these challenges one by one, and we'll try to understand why they occurred, and we'll also discuss how feature engineering helps address all these. Now let's begin with the first consequence of curse of dimensionality, that is distance matrix fail. So many machine learning algorithms such as k nearest neighbor, k means clustering, and several other recommendation system relies on the idea of distance. So they assume that points which are close together are more similar than points that are far apart. So this assumption works well in low dimensional space. For example, imagine a two-dimensional graph. It is usually easy to identify which points are closer and which ones are far apart. But something surprising happens as we keep adding more and more features. In a high dimensional spaces, the distance between different data points begin to look almost the same. The difference between the nearest point and the farthest point becomes increasingly small. Now just think, why does this happen? Because every new feature introduces another independent way in which two data points can differ. When you have dozens or even hundreds of features, it is extremely unlikely for two observations to be similar across all of them, right? As a result, almost every point end up being approximately the same distance from every other point. And when that happens, the concept of nearest neighbor start losing its meaning. If almost every point is equally distant, how can an algorithm reliably determine which observations are actually similar or dissimilar? This is exactly why we say that distance metrics fail in a high dimensional spaces. It's not that distance formula is incorrect. The distance can still be calculated perfectly. The problem is that they no longer provide meaningful information for distinguishing between a similar or a dissimilar observation. And that's a very serious challenge because many machine learning algorithms depend on meaningful distance measurement to make accurate predictions. Now, moving on to the second consequence, that is data sparsity. To understand this, imagine that every feature adds a new dimension to the feature space. So, as we keep adding more features, the size or the volume of that space grows exponentially. However, our data does not magically gain more observations. The number of data points usually stays the same. So, what happens? The existing data points become spread farther and farther apart, making the feature space increasingly empty. In other words, the data becomes sparse. Think of it this way. Imagine placing 100 people inside a small room. Everyone is relatively closer to one another. Now, imagine placing those 100 people across an entire city. The number of people had not changed, but the available space had grown enormously. So, as a result, people became much more isolated. The same phenomena occurs with high dimensional data. As the feature space expands, data points become increasingly isolated, leaving a very few neighboring observations in any local region. So, this kind of sparse data is actually very common in machine learning. And one example is one hot encoded categorical data. If a categorical variable has hundreds or thousands of possible categories, one hot encoding creates hundreds or thousands of binary features where most values are zeros or it's empty. Another example is text data represented using bag of words model. Here, every unique word becomes a feature, resulting in a dataset with thousands of dimensions. Since any single document contains only a small fraction of all possible words, so most entries are again zero or empty. These datasets are therefore high dimensional and highly sparse. When data becomes sparse, traditional distance measures like Euclidean distance becomes much less informative because almost every pair of observations appears similarly distant. So, to address this problem, we often use a different similarity measure which is called cosine similarity. So, instead of comparing the absolute distance between 2 points, cosine similarity compares the angle between their vectors, making it much more effective for measuring similarity in a high dimensional sparse dataset, especially in applications like text mining, document retrieval, or even in a recommendation system. We'll study about cosine similarity in detail later in this course when we work with a high dimensional sparse data. Let's make the idea of data sparsity more concrete with this example. Notice the table on the left, this one. Each row represents a customer and each column represents a feature which is generated through something like one hot encoding. So, what immediately stands out here? Almost every value is zero, right? With only a handful of ones scattered across the table, like here, here, very few ones. Most of them are zero. It means they are empty. So this is exactly what high dimensional sparse data look like. Now imagine that instead of just 10 features, you have 10,000 features, while each customer still has only a few non-zero values. The feature space becomes enormous, but every customer occupies only a tiny corner of it. As a result, customers become increasingly isolated from one another. This leads to a severe practical problem. First, the very idea of similarity begins to break down. Since customers rarely share the same active features, it is difficult to confidently identify who is truly similar to whom. This directly affects k nearest neighbor or KNN because if no meaningful neighbors exist, the algorithm struggles to make reliable predictions. The same issue impacts clustering algorithm as well, like k-means. Instead of discovering clear cohesive groups, the data becomes too scattered to form any meaningful clusters. Recommendation systems also suffers. Whether you are recommending movies like on Netflix, products on Amazon, songs on Spotify, or finding users with similar preferences becomes much more difficult when the data is highly sparse. As a result, recommendation becomes very less accurate. So, data sparsity is not just a mathematical concept, it has a real consequence for machine learning algorithm. That's why for sparse high dimensional data such as one hot encoded features or text represented using bag of words model, we often use specialized similarity measures like cosine similarity, which are much better suited for these kind of data sets. Now, the third consequence of the curse of dimensionality is an increased risk of overfitting. As we add more features to a dataset, we are also giving the model more flexibility. At first, that sounds like a good thing, isn't it? More information should help the model make better decision or better prediction, right? But there is a trade-off. When a model has too many features, especially compared to the amount of training data, it gains enough flexibility to start learning patterns that don't actually exist at all. So instead of capturing the true relationship between the feature and the target variable, the model begins to memorize random noise, outliers, accidental patterns present only in the training data. Think of it like a student preparing for an exam. One student understands the underlying concepts and can solve any new problem with confidence. Another student simply memorizes the answers to the previous year question paper. Both may perform well on familiar questions, but when faced with the newer ones, the student who memorized he will struggle. Machine learning model behaves in much the same way. An overfitted model performs exceptionally well on the training data because it has essentially memorized it. However, when it is exposed to new unseen data, its performance often drops significantly because it has not learned the underlying pattern, rather, it has learned the noise. It has memorized the data or the pattern. So, this problem becomes more common in a high dimensional dataset where there are many features but relatively very few observations or actual patterns. So, that's why in feature engineering, more features do not automatically mean a better model. The goal is to identify the right feature, not simply the largest number of features. In later module, we will explore several feature selection techniques that helps us reduce overfitting by removing unnecessary or informative features before training a model. Now, coming to fourth and final consequence of the curse of dimensionality, that is increased computational cost. Every time we add a new feature to a dataset, we are also increasing the amount of information that the model has to process. Now imagine a dataset with millions of records and hundreds or even thousands of features. For every data point, the algorithm must examine every feature, perform additional calculation, and store more information in memory. As the number of dimensions grows, both the processing time and the memory requirement increases significantly. Some machine learning algorithms are especially affected by this. Take k nearest neighbor for example. To classify just a single new observation, the algorithm has to calculate its distance from every training example across every feature. As the number of dimensions increases, the distance calculation becomes much more expensive. Similarly, clustering algorithms such as k-means will repeatedly compute distance between data points and the cluster centroid during every iteration. With hundreds of features, these computations quickly becomes very intensive. Even many classification algorithm performs additional mathematical operations for every feature while learning from the data. As the dimensionality increases, the training process naturally becomes slower and more resource intensive. So, a high dimensional data does not just make learning more difficult, it also makes learning more expensive in terms of computation, memory, and the training time. This is another important reason why feature engineering focuses on creating informative features and eliminating redundant or irrelevant ones. By reducing unnecessary dimensions, we do not only improve model performance, but we also make machine learning systems faster, more efficient, and easier to scale. We have now explored one of the biggest challenges in working with high dimensional data, that is the curse of dimensionality. We saw how too many features can make data sparse, reduce the usefulness of distance metrics, even increase the risk of overfitting, and significantly raises the computational cost. So, this naturally leads to an important question. If more features aren't always better, then how do we decide which features are actually valuable? That's exactly what this section is all about. We will introduce the concept of feature importance, the process of measuring how much each feature contribute to a machine learning model's prediction. We will begin with correlation, then we will explore mutual information, and finally we will look at modern based feature importance techniques that are widely used in real world machine learning workflows. So by the end of this section, you will know how to identify the features that truly matters and make better decisions when selecting features for your own model. Now that we understand why having too many features can actually hurt a model, the next logical question is, how do we identify the features that are truly useful? This is where the concept of feature importance comes in. Simply put, feature importance measures how valuable each feature is in predicting the target variable. So, not every feature contributes equally. Some features carry a lot of predictive information while others add very little or sometimes even introduce noise that can reduce model performance. So, understanding feature importance helps us understand questions like which features should we keep, which ones should we safely remove, and which features are actually driving the model's prediction. So these insights plays a crucial role in feature selection because our goal is not to use the maximum number of features, it is to use the most informative and task relevant features. So one important thing to remember here is that there is not a single universal way to measure feature importance. Different machine learning algorithm and statistical techniques evaluate feature importance very differently. Each provides its own perspective on how strongly a feature influences the target variable. So in this section, we will explore three widely used approaches: correlation, mutual information, and model-based feature importance. Together, they will give us multiple ways to identify the features that matters most and build simpler, faster, and most accurate machine learning models. Now that we know what feature importance is, the next question is, how do machine learning models actually determine which features are important? The answer is that different model measures importance in very different ways. So let's look at two common examples. First, consider tree-based models such as decision tree and random forest. These models repeatedly split the data into smaller and smaller groups. If a particular feature is chosen near the top of the tree, it usually means that that feature is very effective at separating the data into different branches or splitting the data. In other words, it provides a large amount of useful information right from the beginning. That's why in tree based models, features used earlier in the tree are generally considered more important. Now, let's look at the logistic regression. Unlike decision tree, logistic regression does not split the data. Instead, it learns a mathematical coefficient for every feature. And these coefficient indicates how strongly each feature influence the model's prediction. So, in general, the larger the magnitude of a coefficient, the greater the feature's influence on the decision boundary. Features with small coefficient typically have very less impact on the final prediction. So, the key takeaway is that the feature importance is not computed the same way by every algorithm. Different model looks at the data from very different perspective. and each provides its own way of identifying which features contribute the most to make accurate predictions. Coming up, we will explore some model independent techniques such as correlation and mutual information that helps us measure feature importance even before training many machine learning models. Now let's see how feature importance works in a tree-based model. Imagine we are building a model to predict customer churn. The decision tree always begins with a root node, which represents the very first question the model asks to separate the data. In this example, notice that the root node is service level. Why was this feature chosen first? Because among all the available features, service level provides the best initial split of the data. It separates customer into groups that are most different in terms of their likelihood of churning. Once the first split is made, the model continues asking additional questions. Here, the next splits are based on gender and call charges. So these features are still useful, but they define the group that were already created by the service level. This gives us an important insight. In tree-based models, features used closer to the top of the tree are generally considered more important because they are influencing a large portion of data set. Features appearing deeper in the tree usually affect only a smaller subset of the data. So in this example, service level has the highest feature importance, not because it appears first by chance, but because it performs the most informative and impactful split at the very beginning of the decision making process. This is exactly how tree-based model naturally reveals which features contribute the most to make accurate predictions. Now let's look at another way of measuring feature importance, this time using a regression model. So unlike decision tree, regression model does not split the data into branches. Instead, they learn a mathematical equation where each feature is assigned a coefficient that represents its influence on the prediction. Take a look at this example. Our model predicts whether a loan should be approved using three features: credit score, age, and gender. Notice the coefficient here. Credit score has a coefficient of zero point 0.8, age has a coefficient of zero point 0.1, and gender has a coefficient of 0.05. The coefficient tells us how strongly each feature influences the model's prediction. Here, the credit score had by far the largest coefficient, indicating that it had the greatest impact on whether a loan is approved or rejected. Age still contributes to the prediction, but its influence is much smaller. And gender, which had a coefficient of just 0.05, has a very little influence on the model's decision. The bar chart here, it simply visualizes the same idea. The longer the bar, the greater the feature influence on the prediction. So unlike tree-based model, which determines importance based on where a feature is used in the tree, regression models determine importance by examining the magnitude of the learned coefficient. The key takeaway is that larger coefficient generally indicates more influential feature, helping us understand which variables contribute the most to the model's prediction. So far, we have seen how machine learning models themselves can reveal feature importance. For example, tree-based models identify important features based on where they appear in the tree, while regression model uses the magnitude of their coefficient. But what if we want to estimate feature importance before even training a model? That is where statistical methods becomes very useful. So instead of relying on a machine learning algorithm, these methods examine the relationship between each feature and the target variable using statistical principles. It's important to remember that these methods provides an indication of how informative a feature is. They help us identify features that are likely to be useful, but they don't directly determine the final importance assigned by a trained machine learning model. So in this course, we will focus on two of the most widely used statistical approaches. The first one is correlation, which measures the strength of a linear relationship between a numerical feature and a target variable. And second is mutual information. So unlike correlation, mutual information does not assume any linear relationship. It can measure both linear and non-linear relationship, making it much more flexible to many real-world data sets. So let's begin with correlation and understand how it works and see where it is the right tool for measuring feature importance. Let's begin with the first statistical methods for measuring feature importance, that is correlation. So correlation measures the strength and direction of linear relationship between numerical feature and the target variable. The keyword here is linear. That means correlation works best when changes in the feature are accompanied by a consistent change in the target, following an approximately straight line pattern. For example, imagine we are predicting house prices. If larger house consistently sell for higher prices, then as the area increases, the price also increases in a fairly straight line manner. This indicates a strong positive correlation. Similarly, if increasing one variable constantly causes another one to decrease in a straight line pattern, we have a strong negative correlation. So, whenever a feature and the target move together in a predictable linear way, whether both increases together or one increases while the other decreases, correlation is an excellent measure of feature importance in those cases. One reason correlation is so widely used today is because of its simplicity. It is easier to compute, it is easy to interpret, and it provides a quick indication of whether a numerical feature is likely to be useful or not. That's why it is often used as the first screening tool during exploratory data analysis and feature selection. It helps us quickly identify promising features before moving on to more advanced techniques. Now let's see how Pearson correlation works using a simple example. On the left, we have a small data set containing two numerical variables, year of experience and salary. Notice the pattern in this table. As experience increases, the salary also increases. Someone with 1 year of experience earns 3 lakh. With 2 years, the salary increases to 4 lakhs. Then it increases to 5, 7, 9, and finally 12 lakhs for someone with 10 years of experience. Now, look at the graph on the right hand side. Each point represents one employee from this table. So, as we move from left to right here, the points follows a clear upward trend. They don't fall randomly. They lie close to what looks like a straight line. This is exactly what kind of pattern that Pearson correlation is designed to measure. It asks us very simple question. As one variable changes, does the other also change in a consistent linear manner? In this example, the answer is yes. As experience increases, salary also increases almost proportionally, indicating a strong positive linear relationship. A high positive correlation tells us that experience is likely to be an important feature for predicting salary. Of course, real world data is rarely this perfect. Most datasets contain some variation and noise. But as long as the overall relationship follows a reasonably straight line trend, Pearson correlation provides a simple and effective way to measure the strength of that relationship. Now, let's look at the second statistical method for measuring feature importance, that is mutual information, or we simply write it as MI. So, unlike correlation, mutual information does not assume that the relationship between feature and the target must be linear. This is one of the biggest advantages. Whether the relationship is a straight line, a curve, or follows a much more complex pattern, mutual information can still measure how informative that feature is. Behind the scenes, mutual information is based on the concept from information theory, particularly entropy and information gain. You don't need to understand the mathematical details right now. For this course, what's important is understanding how to interpret the result. So, the core idea is very simple. A feature with high mutual information contains a large amount of useful information about the target variable. In other words, knowing the value of that feature significantly reduces our uncertainty about what the target is likely to be. On the other hand, if a feature has a low mutual information, it tells us very little about the target and is therefore less useful for prediction. The important thing to remember is that mutual information is not limited to only a straight line relationship. It can identify both linear and highly nonlinear relationship, making it a much more versatile feature selection techniques than correlation for many real world applications. There is one final point to be kept in mind. Just like correlation, mutual information is an indicator of feature relevance. A high MIS score tells us that a feature is informative and likely to be useful, but it does not guarantee that a machine learning model will achieve high accuracy using that feature alone. Instead, feature information serves as a powerful screening tool, helping us identify the features that are most likely to contribute to a successful predictive model building. That brings us to the end of Module 1. Before we move on, let's quickly recap what we have learned. So, we begin by understanding what a feature is and saw that feature engineering serves as the bridge between raw and pre processed data and machine learning models. Next, we clarified an important distinction whether a transformation is pre processing or it is a feature engineering, depending on the intent and not code itself. We then explored the Atoms framework, learning that the goal of feature engineering is to improve accuracy, reduce overfitting, optimize training efficiency, and build simpler, more interpretable models. After that, we introduced CTES framework, feature creation, feature transformation, encoding, and selection, which provides a structured view of different types of feature engineering techniques. We also examine the curse of dimensionality and how increasing the number of features can lead to unreliable distance measurement, sparse data, overfitting, and even higher computational cost. Finally, we learned how to evaluate feature importance using both model based approaches and statistical techniques such as correlation and mutual information. So, with these fundamentals in place, we are now ready to move from understanding feature engineering to applying it. In the next module, we will focus on handling numerical data, where you will learn the most widely used feature engineering techniques for numerical features. We will cover topics such as discretization and binning, feature scaling, distribution, transformation, smoothing techniques, and distance and similarity matrices. Most importantly, we will discuss when to use each of these techniques, why it matters, and we'll reinforce every concept through practical examples. I hope you have enjoyed the module, but I'll see you in the next module.